Here's where things get weird. Consider the whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc., etc., etc. Let's ask the question, are there more whole numbers or more perfect squares? Now, first you may think that this is a Bob type question. After all, only certain whole numbers are perfect squares. 4 is 2 squared, 1 is 1 squared, 9 is 3 squared, 16 is 4 squared. Some of my numbers are perfect squares, but a lot of my whole numbers are not. So just like it was in the case with Bob and the kiwis, some kiwis are named Bob, but a lot of kiwis are not named Bob, we would think that the perfect squares have to be less than the whole numbers. But now hold on a moment. What if we use Alice's technique? What if we square each of the whole numbers? That means 1 matches up with 1 squared, which is 1. 2 matches up with 2 squared, which is 4. 3 matches up with 3 squared, which is 9. 4 picks up 4 squared, and that's 16. So according to Alice's technique, because every whole number can match up with a perfect square, the two sets should be equal in size. But the perfect squares are a subset of the whole numbers. Not every whole number is a perfect square, only some of them are. So using Alice's rule, we would say that the two sets are equal in size. For every whole number, there is a perfect square, the same way that for every kiwi, there was a fruit to go with it. But using the Bob situation, we would say that there are more whole numbers than there are perfect squares, because some of the numbers are perfect squares, but not all of them. So who was right? Are the number of perfect squares and the number of whole numbers equal to each other? Or are there more whole numbers than there are perfect squares? Leave your comments in Classroom and tell me what you think.